welcome back everyone. We have 6.3 geometric series. Now, you have technically two learning goals here. I have no idea what happened here. But we are going to be finding the sum of finite geometric series, and we're going to be finding the sum of infinite geometric series, okay? So the sum of finite and the sum of infinite. Okay, now we're going to do a quick arithmetic series refresh, okay? You have your sigma notation, all right, which tells you that you are summing. What are you summing? Like what are you using to find your first and your last term? You're using the explicit rule for the sequence you were trying to sum. Where are you summing from? This is really considered a partial sum from 1 to ever n is, and really it's k to n, because it doesn't have to necessarily be 1, okay? But yeah, it's a partial sum. Now, once you have this piece of information, you have really a formula, and this formula would be called the sum of finite arithmetic series, okay? Where you take n and you multiply by the first and the last term, and you divide by 2, and you can very quickly get the sum of the sequence, okay? Now, with geometric series, all right, and the sum of the finite geometric series, remember, sum of finite, which means we're getting to a number, right? We have a very similar situation. We have, k, we have n, we have our summation notation, right? We use our explicit rule again, but this time it's for geometric sequences, right? And then we have a new formula. This formula is going to be to take the first term and multiply it by 1 minus r to the power of n, and then divide it by 1 minus r, okay? Now, we were going to take some time to derive this if we were in class, because it's a fun activity to derive when you're in class. I might do a side video of deriving this, but for now, this is the formula, okay? All right. Now, the sum of finite geometric series, I'm calling this a we do, okay? Something we've never done. And I'm calling it a we do because when we're doing the sum of finite geometric series, it's so similar to arithmetic, okay? The only difference is now you have this, a of 1 times 1 minus r to the power of n divided by 1 minus r. Double check, yeah, okay? I think you guys can try this without me even showing it to you. So why don't you guys pause it and give it a try. Okay, so hopefully you've given this a try, all right? We have our first term, which is 5. So we can say 5 on the outside, multiply by 1 minus 3 to the power of n being 8. And that would also be divided by 1 minus 3, okay? So you're going to need a calculator for this, all right? I'm going to pull mine up on the side here. And we need to do 1 minus 3 to the power of 8. So 1 minus 3 to the power of 8 gives you, let me move this. Can I also shrink it? No. Oh, dang. Okay. Oh, yeah. There we go. All right. And this is going to be the same thing as 5 times negative 6,560 divided by negative 2. So we're going to divide that by negative 2 right now. And we get 5 times 3,280. Okay. And then we multiply that by 5, and we get 16,400. Okay? So, the sum of the first 8 terms given this sequence, well, given this explicit rule for the geometric sequence, is 16,400. Okay? Once you kind of know what this formula is, it's pretty easy to do. Okay? All right. Now, here is another one. Now, I'm going to have you guys try this one again too, but this is pretty new. All of a sudden, you're used to seeing geometric sequences as written, 1,000, comma, negative 200, comma, positive 40, comma, negative 8, comma, 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 right? When you see it written like this, that's us saying that this is a summation now, okay? That this is a series and you need to sum it, okay? Yes, it still is the same sequence. This is the sequence, 1000, and then this, and then that. It's just like if there was commas there, but when we omit them and we put it as, a sum, we're telling you this is a series, okay? Which means if you want to use the sum of finite geometric series, use this sequence, find your explicit rule, okay? And you know what? I just realized I didn't give you a number to sum it to, so why don't we do it to 8 also? So the 8th term in the sequence, sum to that, okay? Give it a try, and then I'll go over it. All right. Hopefully, given this a try, you're going to want to build your notation. Okay, we're starting at 1. We're going to go to 8. All right. We have our first term, so we want to build this explicit rule, right? Our first term is 1000. And we need to multiply this with r to the power of n minus 1, which really here we keep calling this bottom one k, and so it's really k minus 1. And our r, we're going to get from looking at this. We went from 1000 to 200. Let's forget about the negative there. From 200 to 40. From 40 to 8, right? To me, I mean, you could take 8 over 40 here and divide it, and you're going to get 1 over 5, but I can kind of clearly see this as a divided by 5, and so I know that that must mean it's a 1/5. Now, of course, it's a negative, because it's flipping back between positive and negatives, and so this is my explicit rule, okay? So now that I want to use these series, right, I want to sum the first 8 terms, I just use that formula, a of 1 times 1 minus r to the power of n over 1 minus r, okay? And I plug in the appropriate values. So I get 1000 times 1 minus negative 1/5, okay, to the power of 8, okay? And that'll be divided by 1 minus negative 1/5, okay? Now this is looking a lot more complicated here. And, I should have chose a finer thread for the pencil here, but that's okay, all right? We're gonna have to use our order of operations. We got this power first. Once we take that power, we can 1 minus it, right? Negative becomes a positive. I mean, we could figure all this out, okay? And especially using a calculator. And if you think about this 1/5, right? Maybe for the calculator purpose, it might be easier to make this a decimal. So that's negative 0.2. So if I take negative 0.2 and I bring it to the power of 8, I get 0.000000256, okay? So I'm going to take 1 and I'm going to minus it with that number, okay? And let me just do that real quick. And this is what you should get. All right, in fact, let me write this out. You have 1000, let me adjust that thread, times 0.999999744, okay? A very, very, very small number, all right? And you know what? That's okay. Now you may be thinking, well, shouldn't I round this, Mr. Ferris? Shouldn't I sit here and cut this off? I wait to do my rounding. I wait till the very end, especially since I'm using a calculator. So I'm leaving this in my calculator right now so that I can immediately divide it by the next term, okay? Which here we have a minus situation, right? So this becomes 1 plus 1/5, or 1 plus 0.2. And so we're going to divide by 1.2, okay? So I'm going to divide that by 1.2, and then we need to multiply by 1,000, and we are going to get 833.3312. Now, here we're going to want to round this to the hundreds place, so I'm cutting it off right here. It's between 0 and 4, so this is really just my answer. There is the 833.33, okay? Now you may be thinking that's a weird number to get, but think about this. We're flipping back and forth, and from this point on, we're getting very small, right? In fact, we're getting very, 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 very small, because we're going to go to, You take another fifth of 8, and we're already at a small number, and then another fifth of that number, and another fifth of that number. I mean, this is just going to get close to 0 and never actually cross it, so most of our math is done here anyways, okay? So hopefully you're able to get that one. If not, that's okay. It was a tough one. Now, moving on from finite geometric series and into the infinite geometric series, okay? And so you can see our notation has changed a little bit. We have one starting point going to infinity, all right? And we're still using our explicit rule. What we need to determine is, does the sum converge or does the sum diverge? Now, to simply just tell you, right, and then I'm going to kind of explain these terms, if the absolute value of r is less than 1, right, which means it's between 0 and 1, so like 0.5, 0.3, 0.2, the sum converges. If the absolute value of r is greater than 1, the sum diverges, okay? If the sum diverges, then our sum is just infinity. That's your answer. So if you're looking at this and you look at the r value and the r value is greater than 1, your answer is infinity, okay? If you're looking at this r value and it is between 0 and 1, after you take the absolute value of it, it converges, which means you find the sum by taking the first term and dividing it by 1 minus r, okay? These are in place of this formula. This formula is only for the finite series, which means we're going from 1 to 8, 1 to 20. You know, we have a partial sum. We're cutting off the sequence because the sequence could go on forever, right? Hence why we need to do them forever too, because the sequence can go on forever. That pattern can just continue. Well, let's talk about this converging and this diverging, okay? Okay, so, okay, I got this. Let's do this. All right, let's say, here's just a terribly drawn coordinate plane, okay? And your first, let's use a geometric sequence here. Your first term, is at y of 1, okay? Your second term is at 2. Your third term is at 4. Okay, so, we could sum 1, 2, and 4, but then the next one is 8, and then it's 16, and then it's 32, and then it's 64, and then it's 128, and then it's 256, and 512, and 1024, and 2... Dang it, I can do the next one. Ah, man, I'm getting old. Okay. 2048. 5,120. Okay, all right, whatever. All right, so here's the deal. Notice how this never stops, and we're getting to bigger and bigger and bigger and bigger and bigger and bigger numbers. If the absolute value of r is greater than 1, this situation is going to happen. And if you think about it, if your numbers just continue to get bigger and you try to sum them infinitely, then your answer has to be infinity, right? Because it's just going to be getting to a bigger and a bigger and a bigger and a bigger number, okay? Now let's look at the opposite, okay? Let's say we have another order coordinate plane, right? And this time we start at 8, and then we go to 4, and then we go to 2, and then we go to 1, and then we go to half, and then we go to 0.25, and then 1/4, and then 1/8, and then 1/16, and then 132, and then 164, and then 128, and then 1, and so forth, right? Notice how once we got around here, if we're summing all of these values, it really stops mattering, right? Like if I add 1/128th, and then I add a 1 and 256, and a 1 and 5/12, and it's just getting so infinitesimally small, my sum is not moving anymore. And if this continues for infinity, it's never actually going to push that value anywhere, okay? Now you may be thinking, well, that's kind of odd, because if you're adding numbers for infinity, surely eventually it will get somewhere, right? And that kind of makes even a bigger problem. Like, what about the distance between my two, if I hold two fingers out and I say the distance between these two fingers has an infinite amount of space between it, because if you always take half and half and half, your fingers should never touch, right? This is the kind of part of math that gets weird. We can explain this again. Let's say I have a square. Now I'm having a great time. Let's do this, okay? If I take half of the square, okay, I take half the square. If I take another half of the other half, and another half of that 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 half, and another half of that. Notice how if I sum this half and that fourth, and the half of this, and the half of this, and the half of this, my sum can still not be greater than this, right? Even though I can continue to take half and half and half and half and half forever, right? And if you think of that in terms of area, the area of this still is limited, right? So that, infinitely adding halves of something is not going to get you much further, okay? So, converging, diverging, okay? When doing the sum of infinite series, that is your first question. Is it converging? Is it diverging? All right, so let's do this one. Look at that. Find the sum of infinite geometric series. Determine if the series will converge or diverge. Write your answer in, fraction form this time, okay? So the first thing we need to do is we look at our r. It is 1/3, or 0.33, which means this converges. So we're going to write that. This converges. And if you go back here, we had a formula for that. The first term divided by 1 minus r. So we can sit here, and now we can go, the first term divided by 1 minus r. The first term is 1/9, and that is going to be divided by 1 minus 1/3. Now, if you don't like fractions, it's going to be difficult. Let's do this, okay? 1 minus 1/3, right? This 1 can be converted to a 3/3. I'm using a pointer, so let's do that. Let's write this over here. Let's still have our 1/9, and then we have 3/3 minus 1/3, which is really just 2/3. So this equals 1/9 divided by 2/3. Now, to better visualize the keep, change, flip here, because we're dividing two fractions, I like to write it horizontally. So 1/9 divided by 2/3. Okay, so I have 1/9 multiplied by 3/2. Okay, 1 times 3 is 3. 9 times 2 is 18. That can be simplified, right? 3 goes into 3, 3 goes into 18. So we get 1/6. That is our answer. Okay, this 1/6 right here is the sum of this infinitely, all of its terms. Okay, and that kind of makes sense. Your first term is 1/9, right? And you're off the bat going to take a third of that, and a third of that, and a third of that, and a third of that. Very, very, very small numbers. Okay. All right. Supposed to be a we do, but hey, sue me. Okay, sum of infinite geometric series again, but this time, I'm trying to show it to you every way possible. We have it written from this. So why don't you guys give it a try? Try and build, the explicit rule. And then after you build the explicit rule, build your summation notation, right? Put your explicit rule next to it. See if it converges or diverges, because this is an infinite. So I will write that. Let's write that. You're going to use from 1 to infinity. Okay? So pause it, give it a try. Okay, so hopefully you gave that a try, right? You have a first term of 1.5. Now I know it says to write in fraction form, but we have a decimal. So why don't we just convert that? Let's just make that 3/2. If you use 1.5, not a problem, okay? But I'm a rule follower, so I'm going to follow the directions here, okay? So we have a of 1 times our r value. So we go from 1.5 to -6, from 6 to 24. So to me, this shows we have a multiply by 4, but it's a -4 because we're flipping polarity here. So we get a -4, right? And all this would be to the power of k minus 1, because this k is equal to, okay? So our first question, is it converge or does it diverge? So we look at the r, we take the absolute value of it. Is it greater than 1? Yes, it diverges. So guess what? Done. Answer is done. These numbers will continue to get big forever. The sum is infinity. Okay, let's do this one. All right, find the sum of infinite geometric series. Why don't you guys give it a try? Tell if it's converging, diverging, and then move from there. So pause it, give it a try. All right, hopefully you gave this a try, right? We look here, we have 5/3. This number if we take the absolute value of it, is positive 5/3, which is greater than 1. So, diverges. Boom. Done. Easy day. All right. Now, here we do have the last one, okay? Yep, this is the last one, all right? Which, of course, means it needs to be extra difficult. So we have the sum of infinite geometric series. We need to tell if it converges or diverges. However, we are just given, our series here, all right? So we have our first term, right? So we know, you're supposed to try this first. Okay, oops, long night, long day. So pause it, give it a try, and then I'll go over it. Okay, so hopefully you gave this one a try, all right? We need to find our first term, which is 1. We need to find our r. Now, we very quickly went from 1 to 0.1, which if I did make this a fraction, that's 1/10, right? To 0.01, which if I did make that a fraction, is 1/100th, right? So what could possibly take us from 1 to 1/10, and then also to 1/100th? Now, I, of course, know the answer, but I'm going to use the tools that I've showed you. Pick a number and divide it by the previous. So 1/10 divided by 1, right, which is 1/1. Keep, change, flip. 1/10 times 1/1, right? Well, that's just 1/10. So that must be my r, 1/10. Now, we can, even before we build our rule, we can look at the converging and diverging because we have r, and r is less than 1. So this converges, which means we're going to have to do this problem, okay? And that's all right. We build our summation. So we're going to infinity. We're starting at k is equal to 1. We have our rule, 1 times 1/10 to the power of k minus 1. We even have our formula, right? A of 1 times 1 minus, oh man, I'm doing the wrong formula. Yep. Okay, yep, I'm not crazy. A of 1 divided by 1 minus r, which we technically didn't have to build this to get to that, but you should build that, okay? So we have our first term of 1, we divide it by 1 minus 1/10, okay? Which we're gonna have to do that, so let's convert this to 10/10 so we can actually subtract that. And 10/10 minus 1/10 is 1/9. We write that sideways, so 1 divided by 9/10. Convert that to a 1/1, not a plus sign, it's a 1/1. So 1/1, keep, change, flip to 10/9. And then that just becomes 10/9. And that is your answer, okay? So much longer than 6.2. We had a lot going on here. We had finite, infinite, converging, diverging. Hopefully there's 0 mistakes, but you never know, all right? So, yeah, that was a good one, you guys. I hope you enjoyed it. I hope you learned something, and I will see you next time. Enjoy.